In Essential Task 2.4, we are going to introduce the final phase in research, known as experimental research. Although we've been talking about research now for a few essential tasks, none of the methods that we've described, whether that's surveys, observations, case studies, or correlational research, none of those are classified as an experiment. Today, we're going to talk about what an experiment means, identify some of the strengths, weaknesses, and then, of course, the overall purpose of experimental research. I suggest a horizontal concept map. This is a somewhat lengthy concept map relative to some of the ones we've done recently. It involves what you see here. It entails the two boxes at the top, defining experimental research, and then talking about some important terms related to experimental research. And then at the bottom, there are 5 columns from left to right. I'll go back to the text of the goal, give you a moment to pause so you can copy down the yellow portion of the essential task. But as I alluded to, we are going to first start at the very top and define experimental research. Experimental research is the only type of research that has the ability to prove cause and effect. So we're going to be talking today about randomized controlled trials, other forms of research, specifically experimental research, that try to control for some of the issues we identified with correlational research. We critiqued correlational research because of what we identified back in Essential Task 2.3, the third variable problem. That really won't exist with experimental research because in theory, you're trying to control for some of those issues. As a result, the strength is that this is the only way in this course that we can definitively prove cause and effect. We are actually allowed to use cause here with experimental research. There are 2 weaknesses, and we're going to define what these are in just a moment in the box below. But poorly designed experimental research can sometimes fall victim to what's called confounding variables. Additionally, it's also likely that experimenter bias distorts your findings. Now, luckily, it's easy to control for both of these, but they are 2 examples of weaknesses for experimental research. Continuing onward, we are going to transition down to the second box before we do the 5 columns from left to right, which will identify each of the steps. Typically, I conduct a demonstration at the beginning of class that previews experimenter bias and experiments in general. Due to the nature of the class this year, we won't be doing that, but I do have a debrief on what the demo was from the previous years. But it basically involves me evaluating how quickly people can use their reflexes, but it's an incredibly biased experiment or brief study. Anyway, in terms of the essential task that we're talking about today, one of the first foundational terms is what we call confounding variables. In research, particularly experimental research, the best way to critique an experiment is to identify what are called confounding variables. Confounding variables are any variables that the experimenter fails to adequately control or completely eliminate, which could influence the outcome of your results. And quite frankly, even if it's not definitively clear that they influence the results, even just the possibility, even that 1 iota of doubt can make your entire study invalid. So, for example, if I'm trying to study the effects of light in the environment on your memory, and I have different groups of individuals who are working as my participants, it would be beneficial to try and conduct my study all at about the same time of the day. So, for example, if I've been using noon for all of my studies, I need to make sure if I do it on Monday and Tuesday and Wednesday with different groups, that I conduct the studies at approximately noon. If all of a sudden I conduct my studies at 8 a.m. and then 8 p.m., all of a sudden I've created what's called a confounding variable, where my intention is to only manipulate the light in the environment. But now all of a sudden, somebody reading my study can say, well, there could actually be a big difference between how you react, the condition of your body, between 8 a.m. and 8 p.m. And because you had different trials at very differing times, there's the possibility that other factors, what we call confounding variables, influenced your results. So it's really important, to the best of your ability, that when you conduct an experiment, particularly one with multiple trials, that you try to keep all of the conditions the same, whether that's time of day and a variety of other possible confounding variables. Additionally, there's the possibility of what we call experimenter or researcher bias. They're basically synonyms of each other, where the researcher or the experimenter includes some type of bias in their work, or even if they don't knowingly do it, they could sort of implicitly have some type of bias in their work. This can often happen if that researcher has any financial motivations. So, for example, if I had a brand new drug and I claimed that it treated schizophrenia, one of the disorders we talk about later on, if I was responsible for observing the study and calculating whether or not it actually was effective, the fact that I have some financial interest in the drug working could bias my observations or bias my findings in general. So it's really important to try and disconnect any type of financial motivations between the researcher and the actual science, the actual numbers that you get. We're going to be talking here about the 5 columns that you see under methods. This area off to the right, where sort of that diagonal line is indicated, is not part of this concept map. We are only using the 5 boxes that you see from left to right. We are going to base each of these boxes on the study, does sugar cause hyperactivity? That's kind of a basic study that's been conducted numerous times. It's been replicated over a dozen times. Does sugar cause hyperactivity? So that's the study that we're going to base a lot of what we're about to talk about on. All right, so the first step in order to actually test the question of whether or not sugar causes hyperactivity is to identify the 2 variables involved. In experiments or randomized controlled trials, we're talking about what are called independent and dependent variables, 2 terms that you most definitely saw earlier in your academic career. In just a little bit, we'll define them and I'll talk about what they are. But the first step is to operationally define those 2 variables. Operationally define, or operational definition, is a term that came from the previous essential task, and it involves distinctly and specifically defining the variable, as precise of a definition as possible. Once you have that really precise definition, you can also put together a hypothesis. And I'm sure you've been taught how to write a hypothesis at some point in your academic career. For this class, we're going to do the very simple if-then format. So you notice the if and the then is highlighted in red. But a sample hypothesis for the question about sugar and hyperactivity could be, if a child consumes sugar, then there will be an increase in hyperactivity. That basic hypothesis is what we're going to use to base a little bit of our work on here. And I'll talk a little bit about how to write a hypothesis at the bottom portion of this box. But proceeding down, and just to give you a preview of how much further down this is, we're going to talk about what an independent and dependent variable are. And then there's a mnemonic tip here at the bottom and a box right below it. The box below it's not super long, though. So you've assuredly seen these terms in your academic career. They're terms you use in freshman bio all the way up to whatever you took last year if you took a science, AP bio, or anything of the like. The definitions themselves can be a little wordy, but when you use them, sometimes they just become second nature. But by definition, the independent variable is the variable that the researcher is intentionally, on purpose, deliberately manipulating. So in the context of the study we're describing, that would be sugar, because the experimenter is going to either give people sugar or not give people sugar. They're intentionally manipulating that variable. They actually have a hands-on approach to the independent variable. The dependent variable, on the other hand, is the variable that the researcher is measuring to see whether or not it changes. And what's important here is the researcher is not deliberately influencing this at all. They're kind of sitting back and watching. So I'll give you sugar, that's independent. And then the dependent variable, on the other hand, is the hyperactivity. I'm going to watch your hyperactivity. I'm not going to go and manipulate that. The hyperactivity is just the natural reactions of the participants. The manipulation comes from the sugar being the independent variable. So if you consume sugar, then you'll become hyperactive, is kind of that basic hypothesis. The independent variable in this case is sugar. The dependent variable in this case is hyperactivity. We are measuring hyperactivity to see if that deliberate, intentional manipulation, in this case of sugar, caused a change. As a little bit of a trick here, so if you've, over the course of your academic career, had trouble creating a hypothesis, this tip that I have here, and then I'll go back to the mnemonic, but this tip I think works really well. And in this class, when you have to write if-then statements as a hypothesis, I think this can be of a benefit to you. But every single time you use the word if you do this properly, you are about to identify the independent variable. So to just remove some of the words here, if sugar, then hyperactivity, right? Just make this a 4-word hypothesis. If sugar, then hyperactivity. After the if is always the independent variable. In this case, it is in fact sugar. That's why I matched the green up. As an easy mnemonic there, I look at the letter I in if, and I think of the I in independent. If, then the independent variable, that back-to-back I. Once you write the then, you are about to identify the dependent variable. In this case, it's hyperactivity. That's why you see that kind of purple tint. If sugar, if that green matches up with the if and the independent, then there's hyperactivity. After the then, you have the dependent variable every single time. So if I do that study about lighting and memory, if more lighting, then memory improves. In that case, I am deliberately manipulating lighting in the environment, follows the if. In that case, I'm studying memory, which would be the dependent variable after the then. If that mnemonic's not useful, there's also the one that I propose at the top. If you really grasp that sugar and hyperactivity setup, the independent variable is, of course, the sugar. That's what you put into a cup of coffee. You put sugar into a cup of coffee. So I'm taking that IN in independent and connecting it to that IN in that phrase into the cup. But in either case, those are two mnemonics. So if you've ever struggled with either writing a hypothesis or differentiating independent versus dependent variable, hopefully this example is sufficient for you. As we progress and study this unit, we'll continually add some examples to that. And certainly once you start to evaluate FRQs, you'll be able to practice that skill. In terms of where we're going to this bottom left corner here. It's listed as control variables, and it's the furthest down your concept map is likely to go. Control variables are all of the various variables that you make sure are the same between all of your trials and for all of your participants. Because in theory, if you're going to test if sugar causes hyperactivity, you should have two different groups, one that gets sugar and one that doesn't. But they should be experiencing everything else the same. So they should be in the same room. You should, if it's perfect, conduct the study at about the same time of the day. You should keep the room temperatures the same. You don't want one room to be 85 degrees and another to be 55 degrees. Then all of a sudden their behavior might not be sugar. It might be a result of the room temperature. Lighting in the room. Any possible variable that somebody could reasonably critique needs to be kept the same. Time of day, room temperature, lighting in the room, noise level, those are all reasonable control variables. Like, for example, you shouldn't be playing rock music for one room and then keeping the other room silent. You shouldn't have the TV on violent video games in one room while the TV's playing baseball in another room. You need to make sure all of the other variables are kept the same, reasonably speaking. That way, if you actually find anything, it only has to do with the sugar. It doesn't have to do with the TV, the time of day, room temperature, lighting, sound levels. You can definitively isolate that it was only the sugar that caused that change, because that, in theory, is the only thing that differentiates each of your groups. What you want to do is you want to avoid anything to becoming a confounding variable. Confounding variables make your studies lies, make your studies easily critiqued. We don't want to have easily critiqued experiments here. We want to have really well-designed, controlled experiments. So you set up your variables, independent, dependent. You'll write your hypothesis, and you try your best to keep everything the same. When you conduct an experiment, you're going to have two groups. You're going to have a group that experiences the independent variable, and then a group that doesn't. What we call the experimental group are the individuals in your study, so the subjects, that are going to experience the independent variable. So in the example that we've been working with, those would be the individuals who were provided sugar. So the people that you intentionally gave sugar, they experience the independent variable. Those individuals comprise your experimental group. Alternatively, you also have a group of people that comprise what's called the control group. The control group are individuals who do not experience the independent variable. So in this case, they would not receive the sugar. You need to have a group of people to compare your experimental group to. And that's precisely why we have a control group. One of the most common misconceptions about experimental research, and one of the common mistakes that I see over the years, is somehow looking at the words independent and dependent and think one group gets one, the other group gets the other. That's not how it works. You just isolate the independent variable, which is sugar in this case. And then when you divide your participants, so like the 50 people that showed up to your lab, when you divide those two groups up, 25 people get sugar, 25 people get nothing at all, which in this case would probably be a placebo, so fake sugar. You wouldn't outright tell them they're not getting sugar. You might use a placebo in that case, which would be an appropriate form of deception by giving them a placebo and would have been already approved by the IRB. But you have two groups that get the independent variable and groups that do not. So if it's in the case of sugar, you have groups that get sugar, experimental, and groups that do not get sugar. Oftentimes, particularly when you consume an independent variable, so I'm talking about pharmaceutical drugs or sugar, there's the possibility of what's called the placebo effect. In just utilizing a placebo, a fake treatment or a fake sugar can sometimes gauge this. If you tell people that they're getting sugar and you give them fake sugar, you could see a change in their behavior. They could become more hyper. which would be really alarming because as the researcher, you didn't actually give them sugar. That would be what we call the placebo effect, where people change their behavior not because of the actual substances that they've consumed, but because of their own personal expectations. So, for example, if you're treating something like anxiety, and you're using an experimental randomized control trial, a nice full-blown experiment, to actually test your new pharmaceutical drug, you would give half of your participants your new drug and half of your participants a fake pill. What's important here is you wouldn't tell them that. If the individuals that get the fake pill tell you that their anxiety's dropped, it's probably not a result of the actual drug. It's a result of their personal expectations. And that would be a way of showing you that your drug, at least on a chemical level, probably isn't doing anything. The placebo effect is a really important thing to consider, particularly when testing something like a pharmaceutical drug. We'll talk more about the placebo effect as this year progresses, particularly when we talk about pharmaceutical drugs. In terms of where we are, we have two final remaining boxes, one called random assignment and the other for what we call single versus double blind. But we've identified our variables, we've created a hypothesis, we know what the experimental group's going to look like, we know what the control group's going to look like. If we're testing something like sugar or a pharmaceutical drug, we've considered creating a placebo. Not everything warrants a placebo. If we did study light versus memory, there's no placebo for light. So not everything warrants a placebo. One of the most important, if not the most important part of experiments is what's called random assignment. Random assignment is the process of taking the 50 people for your experiment, so your participants, and breaking them up randomly into the experimental and control group. Meaning, if you have 50 participants, 25 of them get sugar, 25 of them get nothing. It's pivotal that you divide up that group of people with complete randomization, total randomization. You as the experimenter cannot have any influence whatsoever on which individuals go into which group. And you can't do it on some other variable. So you can't say males in one group, females in another. You can't say everybody with a birthday from January to June in one group, everybody else on the other. You can't do that. The division of the participants into the two groups needs to be completely random. You need to shuffle all of the differences between these two groups, which is pivotal. So if there's individuals in your groups that really like candy or really hate candy, individuals in your groups that have certain health conditions, individuals in your group that are different age, it doesn't matter. All of those unique variables that differentiate person to person, through random assignment, they get shuffled up and then spit back out into the control and the experimental group, totally random. And there's a 4-word phrase that you need to memorize. Encode this into long-term memory. This process is done through what's called a computerized random group generator. There is a very common question that you see on the AP exam pretty frequently, and it asks, how would you achieve random assignment? And the answer to that bullet is actually 7 words. Through randomized computer group generator. 5 words. You can add a few more in there. Random assignment is achieved through computerized random group generator. So it's like 7 or 8 words, and that's it. So it's very common to be asked, how do you randomly assign? Which is why I have this in bold, green, underlined in yellow there. That way, you have no control. Genders get randomized, ages get randomized, socioeconomic backgrounds get randomized. Everything about your participants gets totally shuffled. That way, you as the experimenter can't influence what puts an individual into one group over the other. This process, this specific process that we've just outlined, reduces any bias, eliminates the possibility of confounding variables, meaning I didn't accidentally create gender as another variable because I split people up based on gender. And the fact that experiments do this is the reason we can use the word cause. Correlation doesn't have anything like this. The reason correlation is not causation is because it does a very bad job of controlling those extra variables. That third variable problem is a huge issue with correlation. Experiments, though, because you just shuffle everybody up and because you have no influence as the experimenter, all of those weird variables that make each person on Earth unique from each other, because they are shuffled up sufficiently, we can actually look at the results of an experiment and use the word cause. This is the reason experiments are experiments. This is the reason experiments are the only way that we can show cause. It's because we take the time to randomly assign the participants, unlike any of the research methods that we've talked about before. With surveys and with correlation, we randomly select, which is a different step. That's taking 80 people out of 800, as we would do at the school. That's different. This is when you have 50 people already in front of you in the lab, and you need to break them up into 25, 25. How are you going to break up those 50 people? You need to do it randomly through a randomized computer group generator. This is a little mnemonic here, but again, I talked about how random selection a few essential tasks ago. I isolate S for survey, S for selection. With this one, I think about how you already have 50 people in front of you ready to conduct your experiment in your lab. You need to put their ASS into one group or the other. That's what random assignment is. So a little bit of a silly mnemonic here to differentiate the two. But I can't stress enough, it's very common to confuse random selection from essential task 2.2 with random assignment. They are for two very different purposes. Selection is for surveys, SS, or selection is for sampling is for surveys. When we randomly assign, you already have your participants in front of you. You need to break them up into two groups randomly through a randomized computer group generator. The last thing to briefly talk about does not apply to every study. This is specifically useful, again, when doing pharmaceutical drugs or in some circumstances even sugar, but you do not always do this. So these steps only apply when the study warrants it. But the first is what we call single blind procedure. When you use single blind procedure, you do not tell your participants if they've received a placebo or if they've received the real independent variable. This is a good way of seeing whether or not expectations can affect behavior. So this is what I might do if I wanted to study sugar. I would tell the participants, you're all eating candy. We're seeing if sugar causes hyperactivity. But the kids or your participants do not know if they got sugar or if they got sugar-free candy. They're blind to that. Then I, as the researcher, can sit there and try and observe their behavior authentically, meaning the kids aren't going to sit there and say, I got sugar-free candy and be upset. They have no idea. They're going to act like they got regular candy. And then at that point, their behaviors will be more natural. And if I see that those kids that got sugar-free candy act differently, I can say, well, that's not a result of sugar. They didn't get sugar. They don't know that, though. That would be the placebo effect. It is also appropriate to use double-blind procedure, which is the same concept, but the researcher is also blind, meaning I might be testing a new pharmaceutical drug that reduces, let's say, anxiety. I don't want the participants to know if they got the real drug or the fake drug. That's a necessity when studying something like this. But I also, as the researcher, don't want to bias my observations of the participants in the aftermath of taking the pill. So I might be blinded too, meaning I have no idea what anybody got. So I'll take authentic notes, authentically calculate whatever the variable might be. And then after I've authentically calculated my numbers, I can go back in the aftermath and actually be told who got what. Then I can cross-reference my observations and my calculations to which individuals actually got the real drug and which individuals didn't get that real drug. That way, my observation isn't biased. I authentically observed everybody. I might be financially motivated to prove my drug works, but now I had no way of knowing who actually took my drug. So if I do this observation and I say these 10 people saw a reduction in symptoms, and then I find out those 10 people didn't take the real drug, I would then definitively know that my drug probably doesn't work. This step of what we call double-blind procedure can help eliminate any of my bias as the researcher, can help take into consideration the placebo effect, and is absolutely essential when testing new pharmaceutical drugs. That concludes the concept map for today. We'll come back in the next essential task and talk about what's kind of in this bottom right corner. But we've set up our variables. We've differentiated the two groups, the group that gets the independent variable and the group that doesn't. We've randomly assigned our participants, and when appropriate, we've used a blind procedure. There's a video up here, though, that I would like you to watch. I'll include the video on Google Classroom. There's no timestamp because it's only a few minutes long, and I would like you to watch all of it. But it overviews what we are describing here really well.